Obviously, we need to move forward from the heat balance to see what kind of circulations get set up in the desert. So we looked at this just a minute ago in the last podcast with the humidity profile and the potential temperature profile, and we mentioned how during the day you have the unstable stratification near the boundary layer, near the surface, and a well-mixed layer up to the transition zone into the free atmosphere. And at night time we created a stable layer by direct cooling via long wave radiation loss because there are no clouds and so on. So the impact of dust is not totally included here. These are kind of idealistic profiles. How can we look at the circulation? Obviously we can look at the diurnal cycle of the divergence that's associated with this columnar heating and cooling during the day. We can write the horizontal divergence then in terms of the vertical velocity in the pressure coordinate, where V tilde here obviously is the horizontal flow field. What you end up with is something like this. So vertical motion profiles are shown here in 10 to the minus 4 hectopascal per second. That's the in the pressure coordinate. Negative denotes upward motion, so you have negative numbers when the W is upwards because you have pressure decreasing with height, and downward is positive. Calculated from aircraft data collected during summer MONEX experiment flights over Rub al Khali Desert on the Arabian Peninsula way back in the late 70s, I think. In daytime and pre-dawn, these are daytime and pre-dawn, major regions of divergence and convergence are denoted by D and C. So you have convergence here and divergence here, and a little convergence over there as well. The blue arrows represent circulation consistent with the divergent patterns, as we'll discuss in a minute. Nighttime shallow circulation has been added, although it's not evident in the summer MONEX data. Okay, this is from these various papers. So vertical velocity is from this paper of Smith at 1986. So what do you have? During the daytime you have very strong heating of the surface, and that's going to heat the air just above the land, and the air is going to rise. So new air is going to come in to replace the rising air, just like you would have on the ocean rising air when there is heating. But on the ocean typically you have rising air which is also taking evaporated water vapor and then expand and condense and do different things. Whereas here you do have convergence, as you can clearly see here, and you have flow coming in, and this doesn't rise all the way to the upper troposphere as we would have in deep convection on the ocean, but this air is dry, so it's going to rise till it loses its energy, where the divergence begins to occur. What's happening above is that you have radiative cooling, and that's going to be balanced by adiabatic compression and heating. So the radiative loss at the top is still strong even during the day. That's going to create cooler temperatures and sinking. So you can see this downward vertical velocities, or WP, and the two circulation cells in the vertical are going to meet here at basically the region of maximum divergence. Okay, D here. Okay, so it's different, but intuitively it makes sense once you look at it, right? The heating at the surface creating rising sensible heat, dry eddies taking up the warmth from the surface into the atmosphere, creating the mixed layer that we talked about before, this kind of a mixed layer. And then we are going to have cooling and adiabatic compression as the air sinks above. What happens at night time? You get a very different profile of WP and divergence and convergence. So you have very strong nighttime cooling, very strong subsidence, and it's going to come almost all the way down to the boundary layer, and you're going to have divergence at the surface. Okay, so the heat is going to be advected away, and the temperature range on a diurnal time scale over the desert can be very large. So nighttime cooling can produce significant diurnal cycles. So here the WP looks very different. So you have sinking motion all the way down. Okay, this is the basic idea of how the heat balance happens, and we will look at the tropospheric energy budget in a minute, but essentially we will just use the same diagram. So you have convergence and divergence, so you have sensible heating and radiative cooling at the surface or below the mixed layer, and there is dust and radiative heating also playing a role because of the dust, especially if you have black carbon, which can be advected in or locally emitted, and it can have a cooling effect as well, but generally that is not so significant. There is mid-level radiative and sensible heating balancing each other. So this we will see later on produces another unique feature of the desert. And above that you have radiative cooling balancing adiabatic and subsidence and compression and heating. So that's the vertical balance. You can see that there are kind of three layers where the balances are very different. Okay, so we will see the consequences of that in the next podcast. Fairly simple stuff. It's a very short chapter, so you can easily read it, but we will see that the interaction with the monsoon and the nighttime jet are still very interesting in the desert dynamics.